Hello again. This is Math 2233 coming to you from the College of DuPage. And the title of this lecture is Limits and Continuity of Multivariable Functions. As always, please be an active learner as you watch these videos. By way of introduction, remember that we look at things graphically, analytically, and numerically. Let's start with the graph. Remember, this is the free graphing utility I recommended that you use, and here's the address for that. And we're going to look at the graph of z equal f of xy equals sine of x squared plus y squared divided by x squared plus y squared. Now, this is a graph, and x squared plus y squared represents the distance that we are from 0, 0 in the xy plane. And so what happens is this is the radius, and so you're not surprised that this represents the distance, and so we're going to have some symmetries involved. But what happens is that as x and y get further and further away, what happens is it dampens this effect. Now you still have the oscillatory motion of the sine, but since the sine is a bounded function, the further and further you get away, x squared plus y squared is bigger, and so that kind of damps out. But as you get closer and closer to 0, 0, you kind of have this, this emerging bump that happens there that's actually much larger than the other waves that you see. So that's what this picture looks like, and we're going to study this function. So that's a picture of the function in three-dimensional space. Let's look at a different one. This one is z equals f of xy equals x squared minus y squared, all divided by x squared plus y squared. Now again, we're dividing by x squared plus y squared, but the numerator is different, and it's the difference between the two. And when we look at this picture in the standard orientation, we see x coming out here, y over here, and z going up, that this is kind of having wild and crazy behavior. And in fact, when we look at this, we really can't see what's happening near 0, 0. One of the features in your plotting program is that you can rotate things, and so now we're looking into the y direction. So we're looking in through here, and we can actually get some kind of indication of what's happening in that space. So sometimes rotating, it's a good thing, and you have that feature here as well. We can also look at them numerically. So here what we're going to do is we're going to look at f of xy. This was the first one I talked about, and this is the second. We're going to look at different values of x and y. And what we're going to do is, for example, when y is minus 1, we'll take y to be minus 1, x to be minus 1. We substitute that into this, we get 0.455. So these values here are the function values, and these are the values of y, and these are the values of x. And the same thing is true over here for the g of xy. Now, we are studying limits, so we can say, well, gee, what happens as we approach 0, 0? And so what happens is here, the y is getting closer and closer to 0 from the left as I pick these values, and closer to 0 from the right as I pick these values. Similarly, as I pick these values, x is getting closer and closer to 0 from the left, and here it is getting closer and closer to 0 from the right. So this gives us an indication of what the numbers are, in addition to the picture showing us that it looked like that z was getting closer and closer to 1. And if we look at this, what we can see is that for a fixed value of y, let's just say 0, and when x is getting closer and closer, we get closer and closer to 1. Similarly, if we pick a value of y, well, this is y to be 0. So x, as we get closer and closer to 0, this gets closer and closer to 1. Similarly, when we look at the y values, they will get closer and closer to 1 as well. So we have reason to think that this limit is getting closer and closer to 1. So graphically and numerically, we think that is going to be 1. Now let's look at g of xy, and we get closer and closer. But we notice here, as I'm getting closer and closer, I get 1. So whenever I am changing just the x, I get closer and closer to 1. But when I'm looking at the y, I get closer and closer to minus 1. That's a difference. And so I sort of say, that's funny. Maybe this limit doesn't exist. And in fact, we're going to see that this limit is in fact 1, and this limit does not exist. But this was just to motivate the discussion. Let's start now with some basic principles. In fact, before we do that, let's look at another one. Let's look at this one. Now this is more complicated and starts using the notation that we're going to be using as well. So this is z equals f of xy is equal to x times y times cosine of y divided by the whole of 3x squared plus y squared. And we want to say what's happening here. And in fact, the question that's being asked is, what is the limit as xy tends to 0, 0 of that function? And here's the function. It was f of xy is equal to that. So we're going to approach it the same way. Now, if I look at the picture, I can see that it's difficult to tell what's happening with the picture, except there's some major twisting going on. So we'll have to get a handle on that. But we're going to approach in different directions. So we're going to approach 0, 0, which is the limit point that we're approaching along the x-axis. Now, if we're approaching along the x-axis, y is fixed to be 0. And so this is x 0 is f of x0 is 0 for x not equal to 0. And the reason that's true is that if I put y to be 0, I get 0. So this converges to f of xy converges to 0 as xy converges this way. But that is approaching along the x-axis. If I do approaching along the y-axis, what will happen is that I will be taking x to be 0, and so along the y-axis, so this again will get 0. So during both of those axes, this f of xy tends to 0 as xy tends to 0 along those two directions. But now we're going to approach it differently. We're now going to approach it along the line y equal x. Now if I look in my x, y, and z plane, y equal x is this line here. So I'm approaching this on this line in the xy plane. Now, if I'm going along the line where y is equal to x, if I let x equal y, x is equal to y. So this is going to be x squared times cosine of x divided by, and x is y, so 3x squared plus y squared becomes 4x squared. Make sure you understand the simplification that I did there. And now I can cancel out some things. The x squareds will cancel, and I will be left with cosine x over 4. And this is for x not equal to 0. And so now I'm going to take, and again I'm going along this line y equal x, so that is x. So that is as that tends to 0. So this is getting closer and closer to 0. The cosine of 0 is 1, so that gets closer to 1/4. Notice that this number, 1/4, is different than 0. That means that the value we get depends on the trajectory of our approach. That is, this limit does not exist. Now, let's build up some machinery for that then. Let's let f be a function of two variables whose domain D includes the points arbitrary close to the number AB. This is an ordered pair. So you see we're going to be talking about the limit of f of xy as xy in two-dimensional space tends to AB, approaches L, and we write this, that the list limit as xy approaches AB of f of xy equal L if, and yes, this is the epsilon delta definition, the same one that you had before. If for every, from Calc 1 actually, so if for every epsilon greater than 0 there exists a delta greater than 0 such that whenever xy is in D and the distance, now this is the distance formula in two-dimensional space, the distance that x and y are from AB is less than delta, then f of xy minus L is less than epsilon. And again, even though we maybe didn't do many proofs of this in Calc 1, we're going to do a few proofs of this in Calc 3. So this is the definition. You want to be familiar with this definition. This is how you prove a limit exists. So what's going on? Well, we're picking values of xy that are close to AB. So that means the distance is a circle here of radius delta. So we're picking xy in there, and what we get as y values, or not y values, as z values when we plug it into f, is a number that's close to L, and here's where epsilon is. So again, you pick epsilon greater than 0 here, and you try to find delta such that this is true. This is what it looks like using an arrow diagram. This is what it looks like in three-dimensional space. So you see z is f of xy, so here is L. You pick an epsilon interval about that, and you have these values, and you drop the projection into the xy plane, and you get the circle. So this is the calculation that you do. Now, it is important, though, that you know that there are many ways that we can approach this point in the xy plane. We could approach it along this trajectory. We could approach it along this trajectory. We could approach it along this trajectory, and we could even approach it along this trajectory. Any direction will do, because we're in this space. It's not just from the left and from the right. It's from any direction. That makes this a little more complicated. And in fact, here's something to maybe test your understanding. And this is one of the functions that we thought the limit might not exist. So I want you to show that the limit as xy tends to 0, 0 of x squared minus y squared all over x squared plus y squared does not exist. You know what to do. Let's see how you did. And I think we talked about this a little bit, but here is a solution. So we're going to approach 0, 0 along the x-axis. So that means we're going to be approaching it here, 0, 0 along the x-axis. Well, if we do that along the x-axis, that means that y is equal to 0. So if I put y equal to 0 here, I just get x squared over x squared equals 1. So this tends to 1 as we tend to 0, 0 along the x-axis. But now we're going to try to approach the y along the y-axis. And if we go along the y-axis, we're going this way and this way. And so when we're doing that, that means that x is equal to 0. So then we're going to be looking at f of 0y. And that's going to be y minus y squared over y squared is minus 1 for all y. So that means the limit f of x y tends to minus 1 as xy tends to 0, 0 along the y-axis. Now, since in one case we got minus 1, in the other case we got 1, the limit doesn't exist, and that confirms the conjecture we made earlier in the discussion. Here's a more general question. Suppose f of xy equals xy over x squared plus y squared. I ask, does the limit as xy tends to 0, 0 of f of xy exist? If it does exist, you're to tell me what it is and maybe prove that that is the limit. If it doesn't exist, you have to demonstrate that as well. These are kind of essay questions. You know what to do. Let's see how you did. Well, the picture gives you a little bit of indication. This is almost like you're approaching 0, 0 in a cliff, and this is the big cliff that happens. So you're down here on the water, which is way down here, but if you approach it on the other side, you're going to be way up here. So we're thinking this probably doesn't exist because of the big warped picture that we get. But let's go through and see what happens. Okay, so if y is equal to 0, then we substitute f of x0 is 0 over x squared is 0. So this limit f of xy tends to 0 as xy tends to 0, 0 along the x-axis. So we get 0 from that direction. So you see, as we approach 0, 0 along the x-axis, we get f is 0. But now we're going to approach it along the y-axis just to see a different direction. Now, if we're approaching along the y-axis, x is going to be 0, so that we're going to be looking at f of 0y. This is 0 over y squared. That's always going to be 0, so f of xy approaches 0 as xy tends to 0, 0 along the y-axis. So you see we got 0 this way along the x-axis and 0 this way. And so we might be saying, oh, so we're in good shape. But remember the example that we did that had the cosine in it, where it worked again this way on the axis, but we tested something else. So we're going to look at the trajectory again here of y equal x, just to see what happens there. So if we look along the line y equal x, we substitute, and that means if x is equal to y, we're looking at f of xx, we substitute in, we get x squared over x squared plus x squared. Well, that is x squared over 2x squared, which reduces to 1/2. Therefore, this limit is 1/2 as xy tends to 0, 0 along that line. Since we found a trajectory that did not yield the same answer of 0, it was 1/2, this limit does not exist. So when would we use this? For a limit, as a multivariable function approaches a point to exist, the function must approach the same value no matter what path is used to approach the point. Otherwise, the limit does not exist. A land surveyor considers the elevation of different terrains. As a boat travels through a canal on the water, its elevation approaches one value because you're basically going from one level of water to another. As a car approaches the canal from the side, its elevation approaches a higher value because it has to have a higher value of this. So this is giving you an idea of different elevations. Another example, an environmentalist carefully monitors how natural features change over time. The elevation of a river near a waterfall approaches one value from above. You see there's one value up here and another value from below the waterfall. And again, if you see a function that's doing this, you really think it might not be continuous at that area because there is an abrupt and dramatic change in position. The last example here is city engineers plan for expected traffic flow. At a red light, the flow of traffic towards the light approaches 0 at the light. However, the flow of traffic after the red light approaches a positive value as it approaches the light. Okay, here's another problem for you to ponder. If f of xy equals, and this is x, that is y squared over x squared plus y to the fourth, does the limit as xy tends to 0, 0 of f of xy exist? Show that it either does exist or doesn't, and if it does exist, find out what it is. You know what to do. And we'll see how you did when we return. For now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.